Okay, we are on day 2 of our chapter 2 mechanical reviews. Yesterday we got through graphing parabolas and a couple more parabolas, and then we were solving by completing the square. We got into some factoring, which is we were really solving by factoring, and we're going to pick it up with some more solving equations by factoring. Here, so let's zoom in just a little bit here. Might as well use the space we've got. And there we go. So, to factor, these are quadratic equations. We got an x squared, that's our highest power. I want to get everything to one side. 5x squared I'm going to leave, minus 26x I'm going to leave. I'm going to add 1 to both sides, plus 5 equals 0. So once we're on one side, first thing I should do, and I should mention, I always do it in my head, but I need to mention it. If there was a number I could factor out of each of these, I would. If this was 30, I'd divide both sides by 5 now. Or factor out a 5 if it was just an expression, not an equation. So now I multiply these, and I use the plus signs here. This is positive 25. I need two numbers that multiply to be positive 25 that add up to be negative 26. If they multiply to be positive 25, then our magic and add up to be a negative, they have to both be negative. Those are decisions I can make ahead of time. Well, 5 and 5 add up to be 10. The only other possibilities are 1 and 25. Okay. Therefore, we then take this value, put this over 5, and place our reduced result. So this would be x minus 5 times x minus 1/5. But if I notice, x times x is x squared, and I need 5x squared. This 5 will account for that. But conveniently, if I distribute this in to the second factor, I get x minus 5. 5 times x, 5 times 1/5 minus 1. And we may not always show that. We may just kind of do a little sneaky adjustment, just take this 5 and put it in front. So there are our factors. Oops, this is 5x, excuse me. 5 times x, 5x. There are factors equal to 0, so either x minus 5 equals 0, or, so x is 5, or 5x minus 1 is 0, so x is add 1, divide 5. So x is either equal to 1/5 or 5. So that's our process. Let's take a look at 25. I want to get my ends on one side, and I want them to be my n squareds, and I want them to be positive. So I'm going to add 2n squared to this side. I don't necessarily want them to be the left. It just, in this case, that's where my positive n squareds would end up. So I get 6n squared. I want my n's next. I have to add 11 n's to both sides. Plus 11 n's. I've got a plus 4. Now equals 0. If I don't get 0 over there, it's of no use for me to know that a number times a number equals something other than 0. If this was 12, a number times a number equals 12. Well, it could be 1 and 12, negative 2 and negative 6. It could be a half and 24. There's an infinite number of solutions. But if number times a number equals 0, one of the numbers is 0. I need two numbers that add up to be positive 20, or that multiply to be positive 24, add up to be positive 11. 1 and 24 don't. 2 and 12 don't, 3 and 8 do. Positive 3, positive 8. So I put those on 6. And I put those reduced results, x plus 1/2 and x plus 4/3 equals 0, or I check x times x squared. There really needs to be a 6 here. And I'm going to take 2 of that 6 and distribute it here and 3 there. But in effect, all I'm really doing visually is putting that 2 in front and that 3 in front. So I get 2x plus 1 3x plus 4 equals 0. If you happen to be watching this video and you haven't been taught factoring this way, it is quick. You can superfoil, or you can FOIL that out and confirm that we do end up with 6n squared plus 11n plus 4. Therefore, x equals, to solve this, set this equal to 0, solve, I subtract 1, divide 2. Here I subtract 4, divide 3. Okay. More of similar. A little different. First thing I notice is I have to the 4th. But if I have a to the 4th, a to the 2nd, and no x's here, this is still quadratic. If this was 3x to the 100th plus 8x to the 50th minus 3, it's still quadratic. But it's not quadratic on x, it's quadratic on x squared. To find the zeros, they're just saying 0 equals this guy. So I still want factors of negative 9 that add up to be positive 8. If they add up to be a negative, if they multiply to be a negative, and add up to be a positive, I need a positive and a negative. Positive 9, negative 1. So this becomes, I put those on 3, and I place those. This one will just be x plus 3. This would be x minus 1/3, but 1/3, I move the 3 up in front, 3x minus 1 equals 0. However, it's not just x's. Again, as I said, this is quadratic on x squared. Take a quick look, foiling. I get 3x to the 4th. Got it. I get minus an x squared. I get plus 9x squared. Minus an x squared plus 9x squared. Got it. I get plus 3 times minus 1. Got it. So either x squared plus 3 equals 0. That would be x squared equals negative 3. I can't have a squared number equal negative 3. Or 3x squared minus 1 is 0. So x squared is add 1, divide 3. X is, rescue the squared with square root, but not just square root, plus or minus square root of 1/3. That is, I worked myself into a corner here and not leaving room. Oh, I'm not going to do problem 28, so I'm going to work over here. So x is plus or minus square root of 1 on square root of 3, but we do not, it's just a mathematical convention. We don't like having radicals in the denominator if it's reasonably simple to remove them. So I'm going to multiply by root 3 on root 3, and I get x equals plus or minus square root of 3 on plain old 3. That is not part of problem number 28. Okay, let's try another one like that. 29, quadratic on x squared. 0 equals, we're finding 0. So factors of, I can't divide anything from 2, 11, and 21 conveniently. Factors of negative 42 that add up to be, positive 11. So sometimes we might need to list these, but I know if they multiply to be a negative and add up to be a positive, I need a big positive and a little negative. So I might try, 6 and 7. 6 and 7. But if one of those is positive, one of those is negative, the best I can do is get 1 out of it. So I need to get further apart. So I'm going to steal a factor of 3 from this 6. So if I get a 3, 3 times 2 is 6, 2 times 7 is 14, and if those fight, positive, negative, I can get 11. So I need a 14 and a 3. So I put those on 2, and I place them. X squared, quadratic on x squared, careful there, plus 7 times x squared minus 3 halves, or 2x squared minus 3 equals 0. But if squared numbers are always positive, there's no way I can square a number and add 7, not a real number anyway. Can I square a number and add 7 and get 0? But I can square a number, multiply by 2, and then subtract down to 0, I believe. So that is x squared equals add 3, divide 2, x equals plus or minus square root of 3 on square root of 2. Rationalize root 2 on root 2. Why can we do that? Because that is just a fancy form of 1. That equals 1. I'm just multiplying by 1. And I get x equals plus or minus square root of 6 on 2. Can those be reduced? We can never reduce a non-square root with a square root number. So, well, there you go. Divide. We're going to do some long division here. This is going to be important for us in Chapter 2 in the Honors Pre-Calculus portion of this course. We're going to set this up long division just as we were dividing. You know, if I was taking 44 and dividing it by 7, I'd make that 7 goes into 44. So I'm going to take 7a plus 4 into, got to leave room up here to write our solutions, goes into 7a to the third plus, be careful, there are no holes here. We'll address holes if we see those along the way. We're certainly going to deal with those. For instance, if there were no a squareds, I would put plus 0a squared here. But I've got 25a squares, I've got some a's, plus 75a, and I've got a plus 29. And here's how we handle that. That's just rewriting the problem as though we were rewriting 44 divided by 7. So now I say, how many times what do I have to multiply by 7a to get 7a to the third? A squared. And since it's a squared, I'm going to put that in the squared column, a squared. So I multiply a squared times 7a. Just like here, if I'd have said 6, I multiply 6 times 7, put 42 and subtract. Here I'm going to take a squared times 7a, I get 7a cubed. But I also multiply a squared times positive 4 and get plus 4a squared. What did I do next here? I turn that into subtraction. This is positive and positive, so I turn this into minus and minus. The a cubes cancel, they better, that was our purpose. I get 21a squared. Bring down a plus 75a. That's the next thing I would do. Let's say this was 441. I still would have gone 6 here. I get a 2, bring down the 1. I bring down the 75a's. 7a times what is 21a squared plus 3a. 3 times 7, 21. A times a squared. So I get 21a squared. 3a times plus 4 plus 12a. Subtracting those, try to emphasize that, and I get 63a plus 29. I ask, how many times does 7a go into 63a? That is plus 9 times. And I get 63a plus 36. But I am subtracting those, and I'm left with a remainder of negative 7. So my solution is a squared plus 3a plus 9, and we might say remainder of negative 7. But let's say we had 5 into 23. We would say that's 420. We have a remainder of 3. We know that's 3/5. And that's the same as 4 plus 3/5. So this is going to be plus negative or minus 7 on, what are we dividing by? 7a plus 4. So there is our solution. Could be plus negative 7 up top here. That's a little bit awkward with the 7 there. It could either be minus or plus if you want to put the negative 7 up here. Okay, let's try another one. Let's see, do any of these problems have holes? No holes in any of these. I'm going to just set this up, leave some room for my over-the-top solutions. I get 8n plus 5 goes into 24n to the third. I've got some n to the seconds. I've got some plain old n's. And I've got a minus 36. I expect a remainder here because ultimately 5 doesn't divide 36. So let's see what we got. 8n times 3n squared. I'm putting it over the n squareds. 3n squared times 8n is 24n to the third. 3n squared times plus 5 is plus 15n squared. But I am subtracting those. N cubes cancel, of course. 7 minus 15n squareds gives me negative 8n squareds. Bring down a minus 53n. 8n times what is negative 8n? Negative n. Negative n times 8n, negative 8n squared. Negative n times 5 minus or negative 5n. But I am subtracting those. Opposite, opposite. No n squareds. Negative 53 plus 5. Negatives win by 48. Bring down the minus 36. Simple. 8n times what is negative 48n? Negative 6. Negative 6 times 8, negative 48. Between them, there's just the one n. Negative 6 times 5, negative 30. But we are subtracting. N's cancel, that's why we did it. The negatives are stronger than the positives by 6. Negatives win. So we end up with 3n squared minus n minus 6 minus 6 on 8n plus 5. A little crowded in there. I believe I did not move that up very well for you, and I apologize. All the words were good. Hopefully you're able to follow along on that. Here's our process. My mistake. You can pause it here, check and make sure that you're in understanding of what's going on through these steps. Okay, now we are dealing with the number I. This is not a variable. This is an imaginary number, and here is the rule for this. Up until now, we've said that you can't multiply, or you can't take the square root of a negative. Well, if we get to use imaginary numbers, or complex numbers as they're called, complex number has a real portion and an imaginary portion. Here's the rule. I squared is negative 1. It's a number times itself that gets me negative 1. It's not a real number, imaginary number. They are actually used in electronics quite a bit. Imaginary numbers are in circuits. Okay, that means that the square root of negative 1 would be I. So, simplify this. Hey, this is a multiplication problem. I'm going to FOIL. Negative 18. Let's do that again. Negative 18. 3 times negative 3i is minus 9i. 7 times negative 6 is negative 42, and there's an I there. And 7i times negative 3i is negative 21i squared, but I squared is negative 21. I squared is negative 1. Negative 21 times negative 1 is positive 21. Okay. Negative 18, here's a real number. This is really plus 21. These guys are imaginary. I can combine them. Negative 51i. Negative 18 plus 21 is 3 minus 51i. That is called a complex number. I've got a real part and an imaginary part. If you have that, you always put the real part first. That's just a convention. So, apologize for a couple of errors on this video. Hopefully this is making sense to you. Okay, so I could start by distributing, but I kind of like multiplying these together. Maybe you can see ahead and understand why I might want to do that. Minus 5i times 4i is minus 20i squared. But I squared is negative 1. So this is just positive 20 times negative 3 plus 7i. Now when I distribute, I get negative 60, a real part, plus 20 times 7, 140i. Can't combine these. Can't combine the real with the imaginary with addition. You can multiply, That's just 20 groups of 7 imaginaries. Okay. All right, 36. Just to get you started on this, we would have to write this as 1 plus 5i times 1 plus 5i, and then make sure we FOIL. Then we're going to have some terms to combine. Now 36 will be just like 35. Okay, let's jump down to 21. Much like radicals, and number 41, much like radicals, we do not want to have i's in the denominator. So to clean this one up, if this was an I squared, i's would be gone, because I know that I squared is -1. So I'm going to multiply this by I on I. And I get distribute -5i minus 7i squared on -2i squared. But because I squared is -1, this is -5i minus 7 times -1 is plus 7. -2 times -1 is 2. Now, how we would write this in our final form, I want the real portion. The real portion is 7 on 2. The imaginary portion is 5i on 2, and that's how we would represent it. A little trickier, 43. 43, I'm going to use the conjugate here. If this was -4 minus square root of 8, I might multiply by the conjugate of that. So I'm going to multiply by -4 plus 8i. Notice that is not the opposite. The -4 is still -4. Here, -4 plus 8i. You might be saying, why not just multiply by I? Well, when I multiply the denominator by I get a -4i, and the 8i squared becomes okay, but I still have an I. Watch what the conjugate does for us. Here I'm going to get -32i plus 64i squared on, when I FOIL, I get positive 16. Outsides, -32i's. Inside, positive 32i's, and that's why we use conjugates. -32i's, positive 32i's, and finally, a minus 64i squared. Now, could have made, and hopefully you notice this, could have made things a little bit easier with numbers by reducing by 4. All of these I could reduce by 4. I could have made this 2i on -1 minus 2i, and my computations might be a little bit easier. But I'm going to continue with this. I think I'll move to the right. So this becomes real. This is 64 times -1. -64 minus 32i's over, this becomes real, 16 plus 64. We'll continue down here. -64 minus 32i's on 80. Each of these divides by 16. Oh, it would have been so much easier to reduce each by 4 to begin with. But each reduces by 16, so I get -4 minus 2i on 5. Okay, so I won't make that mistake again. If I can reduce, I'm going to reduce. Number 45, I can't reduce. I'm going to use conjugate of the denominator, 1 minus 4i. So I'm still just allowed to divide or to multiply by that fancy form of 1. When I FOIL the numerator, I get a 3. I get minus 12i's. I get plus 1 more I. And I get minus 4i squared. In the denominator, when I FOIL, I get a 1. I get a minus 4i. But I turn around and get a plus 4i. That's why I did it. And ultimately, I get a minus 16i squared. Let's see, real portions. Can we follow this? I squared is -1 times -4 times -4, positive 4, plus 3, 7. I've got -12i's plus an I. -11i's on 1. I squared is -1. times negative 16 plus 16, 17. Final answer, this is good. Better is get the real portion, 7/17, separated from the imaginary portion, 11/17 I. So those are things we're going to need to be aware of for this coming chapter. Okay, then I'm just going to do one more problem from this page, number 40, or from this type of problem. Very, very similar. Order of operations, I'm going to multiply. Negative 56I squared, that's good news. I get a plus 8 and a plus 32I. I squared is negative 1. So this is negative times negative positive 56 plus 8 plus 32I, or 64 plus 32I. Can I reduce that? No. If it was a fraction, yes. If there was an equal to something, I could divide both sides by 32, but you can't reduce it. Don't factor it out. Number 51, I'm not going to complete with you, but again, that is a squared, so we would start out and start our foiling process. Okay, these problems were back on our chapter 1, but we had some challenges with some of these things. So I can treat square roots just like they're variables. So in my eyes, I might be looking at this as negative 2x minus 3y plus 3y minus 2y. I can combine all of those. But the first thing I ought to do is see if I can break anything down. Square root of 5, that 5 is stuck there. 6 is 2 times 3, but I need a pair of 2's or a pair of 3's to do any jailbreaking. So I'm ready just to combine. This is the only root 5 I have. It's stuck. But I have minus 3 of these, plus 3 of these, I have 0 of these things, and now I have minus 2 of these things. At that point, I am done. I want to look at a problem where we might be able to do some jailbreaking, and I noticed in this problem, well, here's one, 18. We can do some jailbreaking in 18. I'm going to leave that one for you because there's a little bit more jailbreaking done over here. I might combine these first, but I'm going to just take a look at square root of 45. 45 in a factor pyramid. 2 doesn't divide it, but 3 does. 3 goes in 15 times, and 3 goes in again 5 times. And there's that hockey stick we talked about in chapter 1. Square root of 45 is 3, got a pair of them, times square root of 5. I could rewrite it as 9 times 5, not square root of 9 is 3. So this is really negative 2 times 3 root 5 minus 3 root 5 minus root 3. Now 20, factor pyramid. 2 goes into that, my lowest prime, 10 times. 2 goes into that, my lowest prime, 5 times. Nothing goes into 5. So the square root of 20 minus square root of 20 is minus 2 root 5. So what do I have? Negative 6 root 5s minus 3 root 5s minus 2 more root 5s and a plain old minus root 3. So I got a bunch of minus root 5s. Minus 6 minus 3 minus 2. That's negative 9, negative 11 root 5s and a minus root 3. Okay. Wrap up a few examples on this page and then we'll cut to our finish the last video on one more section. We got another page to go after this. Okay, we do not want radicals in the denominator. But anytime we're presented with a fractional situation, everything's factors, there's no addition, subtraction, I want to try to make numbers smaller. And the ways I can make numbers smaller is, if I could reduce 5 and 16 because they're in square roots, I'd reduce them. Now let's make this clear. If this 5 was let's say 15, I couldn't reduce this 15 with this 3 because we got a square root versus a non-square root. So I can reduce by fraction. I can jailbreak, so maybe 16, I might be able to jailbreak 16, or I can do what I call the V8 moment, which is once I start jailbreaking, I discover, holy smokes, I was dealing with a perfect square, why did I waste my time? Square root of 16 is 4, so this is just root 5 on 3 times 4, or root 5 on 12. And that's it. Number 59. Reduce by fraction. Even if this was 33, I couldn't reduce 3 and 33, but I can reduce root 2 and root 16. I can reduce those by 2. So I get 3 on root 2 and root 32. I get 3, the root 2 reduces this by 2, root 16, and root 16, there it is, that's a V8 moment. I'm not going to multiply root 16 on root 16 until I make my number smaller. That is just 3/4. Okay. Number 61, reduce by fractions. Well, the 2's reduce. They're not square roots. 12 and 64 both reduced by 4. Square root of 3 on 16. Square root of 16, we're specializing right now. Square root of 3 on 4. Okay, let's go ahead and wrap this one up. I think I got time to do this guy. Okay, one more example here. Square root of 5 on square root of 45. 5's reduced. I get square root of 1 on square root of 9. But square root of 1 is 1. Square root of 9 is 3. Number 65. When I distribute, I get 3 times square root of 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 3. I might have missed that problem for you too. I'm a little offset today on my camera. Apologize for that. I need to do a better job of checking this. I get 3 square root of 3 times 3 root 3 is square root of is 3 times square root of 9. But square root of 3 times square root of 3 square root of 9 is just another 3. Square root of 3 times 5 plus 5 root 3 for 9 plus 5 root 3. That is not 14 square root of 3's. That's a plain old 9 plus 5 root 3. So let's jump down to number, ooh, this one's worth doing. Let's do 67. Here I get distribute 3 times square root of 6 times 2, 12, plus square root of 6 times square root of 3, square root of 18, and we got some jailbreaking. 12 is 4 times 3, and the square root of 4 is 2. So I can take 2 times 3, 6, but the 3 is stuck. 18 is 9 times 2, and the square root of 9 is 3, but the 2 is stuck in jail. I can't call this 9 root 5's. This is 6 apples plus 3 oranges. They are not like terms, can't combine them. Number 69, FOIL. You might jailbreak, but let's say I didn't recognize that I could just call this plain old 2. I get square root of 12. I get plus 5 root 6. I get minus 2 times this is just one of those, minus 2 times root 8, and minus 10 times root 4, but root 4 is just 2. And we say, wow, I can't combine any of these. Well, maybe we can. Let's see. Square root of 12. Again, I could have jailbreaked or V8 momented this 4. Square root of 4 is 2, but let's say I didn't. I recognize this is 4 times 3. That's 2 root 3. 6. Can't do anything with that. 8. That is 4 times 2. I've got minus 2, but square root of 4 is 2. 2 times 2, 4. So minus 4, but this 2 is stuck in jail. And here I have a 10 times 2 minus 20. And we are simplified, and I cannot combine. A little surprising. Okay, you have solutions on here. Please make sure you are checking your answers. Those were provided for you so we could be certain you are in good shape on these. All right, good luck with this.